Hello, everybody. I wanted to walk through basically the PowerPoint presentation that I had prepared. This is just a series of practice problems. I wanted to give you all this recording so that basically you can watch it on your own time and pace yourself accordingly. If there's something that you understand really well, then spend some more, or don't spend any excessive time on it. But if it's something that you're struggling with a little bit, spend a little bit more time on it. Okay, so my PowerPoint is going to begin sharing, and there we go, and recording is going. Okay, so one important feedstock molecule that can be derived from biomass is known as 2-propanol, C3H7OH. If 423 moles of this compound are needed for a reaction, how many kilograms of C3H7 OH be used? Okay, so we're going from moles to grams to kilograms. Now, what we need to know and what we need to remember is that there are 1,000 grams of anything in 1 kilogram. Now, we know that we have 423 moles of C3H7OH. We need to get to grams, and subsequently we need to get to kilograms. Now, what's worth noting is for this sort of problem, you definitely need a periodic table. There are some pieces of information that I remember, and I can go ahead and use those here. For example, the molar mass of carbon is 12 grams. The molar mass of hydrogen is 1 gram. The molar mass of oxygen is 16 grams. So what we need to do is basically say, how many carbons do we have in this compound, C3H7OH? Well, we've got 3 carbons, so we're going to multiply 3 by 12. To that, we're going to add, well, there's a total of 8 hydrogens. There's 7 and then 8 hydrogens, so 8 times 1. To that, we're then going to add 16. So the molar mass of this compound, C3H7OH, is 36 plus 8 plus 16. That amounts to 36 plus 8 is 44, plus 16 is 60 grams. So we have our conversion now, which I'm going to erase this math that I just did, because we have the information that we need. And I'm going to write basically the definition that we now have. That is 1 mole of C3H7OH is 60 grams. Now, I'm going to use this 423, and I'm going to do what's called dimensional analysis to say 423 moles is on top, on bottom, 1 mole. And this is in reference to my C3H. I'm going to go ahead and just call it 8 because there's 8 hydrogens. O. C3H8O is 60 grams. The next thing that I want to do in this dimensional analysis, I want to take into account my conversion from grams to kilograms. And so what I'm going to do is I'm going to say my next definition, my next equality statement, my next conversion factor, and that is that there are 1,000 grams in 1 kilogram. So basically, if I multiply everything across the top and then divide by everything on the bottom, I will get my answer. So 423 times 60, plug that in the old calculator, 423 times 60 is 25,380. I divide that by 1,000. And I'm dividing that by 1,000 so that I can go from grams to kilograms. And the answer to this is 25.38 kilograms. So there's my answer. 25.38 kilograms of C3H7 or H8O. So another problem that we'll see is another sort of conversion. A 245.3 gram sample of glutamic acid, which has a formula of this, is recovered from an experiment using fermentation to convert biomass. So we have how many moles of C5H9NO4? Well, now what we're going to do is we're going to go from grams to moles. So we're going to write 245.3 grams of C5H9NO4. Now we've got to figure out our molar mass of this substance. And what we'll find is that carbon is still 12. Hydrogen is still 1. Nitrogen has a molar mass of 14, and oxygen is 16. So now what we need to do is say 5 times 12 plus 9 times 1 plus 1 times 14, or just plus 14, plus 16 times 4. So we'll go to our calculator and say, what is 5 times 12? Because we have 12, or we have 5 carbon atoms. That's 60. So I'm going to keep these numbers in at the bottom here so I can keep track of them. 60 plus 9 times 1 is 9. Plus, now I've got to go to, so I've accounted for the carbons, I've accounted for the hydrogens, nitrogens, 14. Cross that out. Plus 16 for oxygen, but we got 4 of them, so plus 64. So 60 plus 9 plus 14 plus 64 equals 147. So 147 grams of this substance, C5H9NO4, is 1 mole of C5H9NO4. Okay, this question is asking for a number of moles. And you know what? Grams of the C5H9NO4 cancel out. We're left with moles. So all that we need to do is take 245.3. And think about this before we do any sort of calculation. If 1 mole of this substance is 147 grams, and we have 245 grams of it, do we have less than 1 mole? Do we have exactly 1 mole? Do we have more than 1 mole? We have more than 1 mole, okay? So we'll do 245.3 divided by 147 equals 1.668, which I'm going to go ahead and just call 1.67 moles of the substance. Okay, now this question, this second question, this is a super important question, and it's pretty challenging, but we can do it. So the question is, how many atoms of hydrogen are in this sample? Now, let's think about our molecule. Our molecule is C5H9. This doesn't have an eraser function. Let's see. Eraser function, done. Pen function, oopsies. H5NO4, that's an N. And this compound, if we have 1 molecule of it, we have 9 H atoms. Okay, now let's say that we have 2 molecules of this. How many hydrogen atoms do you have? 18. If you have 3, you got 27 hydrogen atoms. What if you have 10 million of that molecule? Well, 10 million times 9. Each molecule has 9 hydrogen atoms, so you'd have 90 million, right? Now, we are talking about this in the context of moles there. So let's say you have 1 mole of this compound. You have 9 times 6.02 times 10 to the 23rd. This sample, we have 1.67 moles of molecule, of this molecule. Okay, so if we have 1 mole of this molecule, we have 6.02 times 10 to the 23rd molecules. Okay, so this gives us our conversion from moles to molecules. Now we need to go from, well, if we have 1 molecule, how many atoms of this do we have? 9 hydrogen atoms. So what we're going to do is say 1.67 times 6.02 times 10 to the 23rd times 9, and that's going to be our answer. So for the purposes of the illustration, I'm going to punch this into my calculator using the big screen. So 1.67 times 6.02, so that's 3. Nope, my calculator actually doesn't even show that. So let me see this again. Clear, clear, clear. So 1.67 times 6.022 double E to the 23rd times 9. And my answer ends up being 9.05 times 10 to the 24th hydrogen atoms. So that's an absolutely massive number because we took our number of moles times Avogadro's number times 9 to get us the total number of atoms, because we had taken into account how many hydrogen atoms are there in each one of these molecules. Okay, so that's the sort of question you should anticipate for your exam. These are challenging questions, but they're totally doable. You just have to keep track of everything that you're doing. So I strongly recommend doing this problem multiple times so that you process each part of it. This second problem, how many atoms of hydrogen are in this sample? Well, do the exact same calculation, but change it from hydrogen atoms to carbon atoms, from carbon atoms to oxygen atoms, to nitrogen atoms, to carbon and hydrogen atoms. See if you can work within the parameters of what we've done here to answer this question, or to answer these new questions, make up new questions for yourself. Okay, so now we need to move on to a little bit of a nomenclature review. Simple anions have, for instance, chlorine have this IDE suffix. Now that IDE ending indicates a binary compound, so a compound that's composed of 2 elements. There are oxyanions, which we've talked about a little bit. Specifically, we talked about chlorate, that family of oxyanions: perchlorate, chlorite, chlorite, hypochlorite. There are 6 ATE ions that you learn in chapter number 2. Now, classifying each of the following compounds as an acid, a base, or a salt. Okay, keep in mind our definitions for acids. Acids are substances that can donate a hydrogen ion or a proton. And bases, so whenever you're thinking of an acid, you should basically look at something like HCl is a good acid. NaOH is a good base. These are strong acids and bases, respectively. Now, the hallmark for an acid, you got to have that hydrogen ion, that free hydrogen, that hydrogen that's only by itself, or sorry, that hydrogen that's with an anion. A base, you should be looking for OH, okay? Now let's look at each one of these, or at these two different compounds. HF, is that similar to HCl? Yes, it is. That's one of, that is an acid. It is not a strong acid. This is an example of an acid because this HF will dissociate. And considering the fact that fluorine and chlorine are in the same family or the same group in the periodic table, they're going to behave similarly. So yes, HF is an acid. So basically that gives us the opportunity to omit two answer options. Now we're left with KNO3 and KNO3 as a base or as a salt. Now, answer options A and B are what we're left with because they both confirm that HF is an acid. Now, looking at KNO3, is that a hydroxide? Does that have OH? Simple question, not a trick question. So KNO3, is that a base or is that a salt? Well, the question is, does it have a hydroxide? KNO3 is not a trick question. It does not have an OH. It has an oxygen, but not an oxygen and a hydrogen. So this is a salt. So B is your correct answer. Now, electrolytes. Well, let's go through and just classify each of these compounds as an acid or a base. So are there any that have hydroxides? Yes, there are. Well, NaOH, base. Then we've got CH3OH. Okay, this is a little bit of a tricky question because I asked if there were any OHs, and the answer was yes. But this is actually a molecular compound. And the reason that it is because compare NaOH to CH3OH. CH3, carbon, that's a nonmetal. Sodium, that's a metal. So when we're looking at a strong acid or a strong base, or sorry, a strong base, you should look for OH, and then the other thing that it's associated with, or the other ion, that should be a metal. So CH3OH is a molecular compound. Okay, now let's go to, well, the second option, MgBr2. That's magnesium and bromide. This is a salt. This is an ionic compound. Next up is HNO3. This is nitric acid. This is one of your 7 strong acids. So this is an acid. The last one is HF. HF, we saw in the previous slide, it is an acid. What's tricky about this is I'm going to go now to the next category. Strong, weak, or non-electrolyte. Excuse me. If something is a strong acid, it is a strong electrolyte. If something is a strong base, it is a strong electrolyte. If it's a weak base or a weak acid, it is a weak electrolyte. So HF, yes, it's an acid, but it's a weak acid. So this is a weak electrolyte. CH3OH, as a molecular compound, this is a non-electrolyte. So a molecular compound is a non-electrolyte. HNO3 is one of your strong acids, so that is a strong electrolyte. MgBr2, well, let's see, magnesium bromide. This is an electrolyte. It is an ionic compound. And this, we would go ahead and classify it as a strong electrolyte. Next up, sodium hydroxide, being a strong base, it is a strong electrolyte. So you're going to see all the things that we just said displayed here. And that confirms everything. So that last compound was magnesium bromide, the last one that we kind of looked at. And that's generally going to be involved in a type of reaction known as a precipitation reaction. So precipitation reactions, we talked about these a little bit. And these compounds are compounds that have soluble substances. So if you looked at them, you wouldn't really notice any solids in them. So one back here is potassium iodide. That's got potassium ions and iodide ions. The other is lead nitrate. So Ki and PbNO3. Now these are separate from one another, but when they get pooled together, a solid begins to form. Now, what is that solid? Well, there's a kind of formula for what's known as a precipitation reaction. And that is you have an anion and a cation that they don't form a solid, as we see with potassium iodide and lead nitrate. But then when you mix them differently, these two different cations and anions interact. So what we have is lead and iodide interacting with one another. And when they interact with one another, they form a solid. That solid is potassium iodide. Potassium iodide precipitates out of solution. It forms a solid. It clumps up. It falls to the bottom of the container. Whereas the potassium ions and the nitrate ions, they continue floating around. They'll come in contact with one another, but they'll just dissipate. They'll bump in, but then leave. So anytime we're talking about a solution, we always want to be thoughtful of, is this a precipitation reaction? Is there a solid that's going to form? Is there something insoluble that's going to form from this reaction? Now I'm going to go ahead and stop here to end part 1 of our discussion. I'm going to post this video, and then the second one will come later on, where I'm going through slides numbers 8 through 19. All right, have a good one.